You are looking at the most recent image of the cosmic microwave background radiation, the first visible light in the entire universe. Long since faded from the visible part of the spectrum, the photons that make up the cosmic microwave background, or CMB, have been traveling through space since the universe was less than 500,000 years old. Even with being so faint and difficult to capture, this light still has a story to tell us. It holds a wealth of information that can give scientists insight into the very beginning of time, the distribution of matter in the universe, the expansion rate of space, and it even gives astronomers insights into how everything might end. Welcome to the story, my story of light, the thing that captures my imagination more than anything else in physics. And I figured what best way to start off a YouTube series about my favorite thing in physics than with my favorite picture of my favorite thing, the cosmic microwave background radiation, the first light, visible light, that ever existed. But to truly appreciate just what's going on in this image and the importance of it, we need to be as cliche as possible and go back to the beginning, the very, very beginning, when the universe was 10 to the minus 43 seconds old. Modern physics doesn't yet have the ability to really understand what's going on with the universe before this point in time. See, anything before 10 to the minus 43 seconds old, the universe is infinitely hot, it's infinitely dense, and the four fundamental forces, gravity, the strong, weak nuclear force, the electromagnetic force, are all unified into one single fundamental force. But after 10 to the minus 43 seconds, things change. The universe rapidly expands, gravity separates from the four fundamental forces, and eventually they all separate from each other. If photons, or light, appear soon, and I mean very soon after the very beginning of time, between 10 to the minus 36 and 10 to the minus 32 seconds. After the universe was only 10 seconds, the photon epoch began, when they dominated the energy in the universe. Something to understand here is that even though there was light, there wasn't visible light. And chances are, if the algorithm sent you here, you're aware that the entire spectrum of light doesn't just constitute visible light. The electromagnetic spectrum ranges from everything from the gamma rays, which are very high energy, small wavelengths, somewhere around 10 to the minus 12 meters, the stuff of my nightmares, all the way to the low energy, very long wavelengths, radio and microwaves. Those can range anywhere from a few millimeters to miles or kilometers in length. Invisible light, on the other hand, occupies just a tiny little sliver of the entire electromagnetic spectrum, somewhere around 380 nanometers to 700 nanometers. And shortly after the Big Bang, at those very early stages of the universe, the temperature and the density was such that it was just impossible for visible light to exist. Now, the cosmos would stay this way, too hot and too dense for visible light, for a long time after the Big Bang. For the first 380,000 years or so, space was filled with a hot, thick, opaque fog of superheated subatomic particles. Free electrons were constantly interacting with any photons that would have been created at that point, thus hindering the progress of any light. But at around 370,000 to 380,000 years, something changed. Space finally had expanded and cooled to a nice balmy 3,000 Kelvin, down from the billion or so Kelvin it was just a few 100,000 years earlier. At this point, electrons could finally bond with protons and form the first neutral atoms. This is known as the recombination era, when the first neutral hydrogen and helium atoms appeared. This change allowed for those early atoms that formed to enter their lowest energy state. This low energy state meant that excess energy would be released via photons. And because these neutral atoms could scatter thermal radiation, the universe became transparent to light. This all happened when the cosmos was just a fraction of its current size. And the light scattered from newly formed atoms is similar to how light scatters off the surface of clouds on a stormy day. This meant that for the first time in all of time, visible light existed, and the universe was filled with it. But this wasn't the light from stars or galaxies. There were still millions of years before those would form. This was something else. This was light from the very beginning of time. It was the fingerprint of the Big Bang itself. With the ever-expanding and cooling space, this light could not last forever, and over time it would slowly fade away as the wavelengths stretched from the visible part of the spectrum to the infrared, and eventually to the micro and radio waves. Once again, the cosmos was void of light, and the universe had entered its cosmic dark ages. The universe remained in the cosmic dark ages for millions of years until the first stars formed. And one by one, those first stars cut through the black void of space, and the cosmic dark ages came to an end, millions of years after the cosmic microwave background had faded. But there were still traces of the CMB. They just couldn't be seen. Billions of years of cosmic and biological evolution later, our little species on our tiny planet somehow, someway predicted that light still existed. And somehow we found a way to detect it and let it shine once more. Let's go ahead and jump ahead a few billion years to the early 20th century, when an astronomer by the name of Henrietta Swan Leavitt would develop the first reliable way to calculate distances between us and distant objects in the universe. Henrietta Swan Leavitt was working at Harvard University as a computer. Literally, she was a computer, someone who computed or performed mathematical computations before calculators were invented. During that time, Leavitt had begun working for Edward Pickering, the observatory director who tasked her with studying the small and large Magellanic Clouds. During her studies, she identified 1,800 variable stars, with 47 of them being a type of star known as a Cepheid variable. These stars vary in brightness over the course of days or weeks, and Leavitt realized something very special about these stars. She found that the longer the period or pulsation, the brighter the star intrinsically is. Upon realizing that if she knew just how bright a star intrinsically was, she could compare it to how bright it appeared to us, and then use the inverse square law to calculate the distance between us and that star. This work was published in 1912 under the authorship of Pickering, but the open lines stated that it was prepared by Miss Leavitt. This discovery was among the most important breakthroughs in the history of astronomy. It set the stage for all of modern cosmology. Being able to figure out the distance between us and very, very far off objects meant that we had the ability to study the universe on a massive scale and get the true size of it. Her work didn't only set the stage for modern cosmology, but also the eventual development of the Big Bang theory, in which the cosmic microwave background plays an integral part. Sadly, Henrietta Leavitt passed away in 1921 at the age of 53 due to cancer, and today we know to credit her with the first standard candle. As the 20th century marched on, astronomers were still torn on how the universe began. Many favored a universe that was essentially a steady state universe, one that has always existed and always will, and that has largely looked the same. One way to look at an unchanging universe is the static one. This type of cosmology means that the universe stays largely the same forever. New stars form at roughly the same rate old stars die out. It's neither expanding or shrinking. Albert Einstein was actually fond of a static universe, and he proposed a steady-state static model of the universe in 1917. However, the math quickly showed that that just wasn't a possibility. A static universe would ultimately be unstable. Furthermore, there was undeniable evidence that the universe wasn't static, but in fact expanding. Evidence could be found in the equations of relativity. Physicists such as Alexander Friedmann had been able to derive an expansion rate just from working within the mathematics of relativity. But it wasn't just the math. There were visual observations that showed distant objects were moving further away from us. Vesto Slipher was an American astronomer who, in 1917, was the first to measure the radial velocity, or line-of-sight velocity, of over 24 distant objects in outer space. At the time, these objects were known as spiral nebulae for obvious reasons. They were shaped like spirals. Although we now know them to be other galaxies, Slipher would go on to find that all but 3 of them had light that was redshifted, meaning they were moving away from us. As you're probably aware, the Doppler effect is observed in light as well as sound. With sound, a common example is a car horn as a car is moving closer to you will actually sound as though it's getting higher in pitch. And then as the car moves away from you, the car horn is going to sound as though it's getting lower in pitch because those sound waves, as it comes towards you, are getting compressed, whereas as they move away from you, they're getting stretched out. Light behaves in a similar manner. As you're getting closer to a source of light, the light waves are going to be compressed and shifted towards the blue end of the spectrum, whereas when you're getting further away from a source of light, they're going to be shifted towards the red end of the spectrum. So when Slipher observed that these distant spiral nebulae were all red shifted, it meant that they had to be moving away from us. And it seemed to be a common property of all of these distant structures, and it pointed at something very different than a static universe. Being able to use light to calculate the distance between us to other astronomical objects, and using the light's shift towards the red or the blue to see if an object is moving further away from us or getting closer, were all methods that allowed a young astronomer from Missouri named Edwin Hubble to eventually demonstrate that the universe was not only much bigger than we thought, but that it was actually getting bigger. By the 1920s, the Mount Wilson Observatory in California welcomed a newly completed 2.5-meter telescope. That's 100 inches for my fellow Americans. Around the time this telescope was completed, Edwin Hubble arrived at the facility and began observing distant spiral nebulae. Using the standard candle developed by Leavitt and building on Slipher's work from years earlier, Hubble showed two important things. One, by using a variable star discovered in the Andromeda Nebula, as it was called at that time, Hubble found that the Andromeda Nebula was over 900,000 light years from us, meaning that it couldn't be part of the Milky Way. And we now know that the Andromeda Nebula is, in fact, the Andromeda Galaxy, and it is over 2 million light years away from us. Hubble had discovered the universe was made up of not just the Milky Way, but these spiral structures were actually other galaxies, island universes as they've often been called. At the end of it all, Hubble had been able to calculate the distance to objects 20 million light years out. Second of all, Hubble showed that without a doubt, the further away a galaxy is from us, the faster it's moving away, and that it does so in a linear fashion. Thus, Hubble's constant was born. To say that Edwin Hubble's discovery would play a large role in astronomy is downplaying it. Hubble's law would become vital to understanding our universe on the largest scale. Published in 1929, this would lay the groundwork for a Belgian physicist's primeval atom theory to eventually become the basis for modern cosmology and the discovery of the cosmic microwave background. See, in 1927, just a couple of years before Hubble had actually published his work, there was a Belgian physicist by the name of Georges Lemaitre. I am really sorry about my pronunciation of his name. I speak Spanish and English. It's going to be that bad throughout the rest of this video, just to prepare you. And he had been able to derive the expansion rate of the universe, which matched Hubble's constant independently from Hubble, before Hubble, by what he found in relativity. Once Hubble's work became well known, Georges Lemaitre was able to use it to explain the redshifts of distant objects and propose his primeval atom hypothesis. In 1931, Georges Lemaitre hypothesized that at some point in the distant past, the entire universe was contained within a small point he called the primeval atom. And our universe began when this atom expanded rapidly, leading to the cosmos that we saw today. Among the important predictions that the Big Bang Theory made was that it would have left behind a fingerprint of sorts, some sort of evidence of the event. Lemaitre expected that it would be in the form of cosmic rays, and he actually did find cosmic rays, but they weren't from the Big Bang. They were localized to our galaxy. But it was in 1948 when Ralph Alpher, Robert Herman, and George Gamow, who had been studying nucleosynthesis of light elements in the early universe, found that said nucleosynthesis would have required a Big Bang that would have been hot enough to leave behind remnants of the event, and those remnants should still be detectable. Alpher and Herman determined that the radiation would sit no higher than 5 Kelvin, consistent with microwaves. Unfortunately, at this time, there was insufficient technology to detect this radiation, and Georges Lemaitre would have to wait until just about 2 years before his death to see that remnant light he predicted be detected. In 1964, Bell Labs in Homedale, New Jersey, was base camp for 2 radio astronomers by the name of Arno Penzias and Robert Wilson. Wanting to listen to other noise from outer space, the duo was surprised to find a low hum wherever they aimed their radio telescope. Wanting to ensure that there was nothing man-made being picked up by the sensitive equipment, they went to great lengths to ensure that whatever it was that was not coming from outer space could be accounted for. However, no matter what they did, that hum was still there. This hum was uniform in a way that meant it couldn't be local. It seemed to be spread across evenly throughout the sky. They detected it no matter where they pointed their telescope. It had to be coming from way out there. At the same time, James Peebles of Princeton University was studying cosmic expansion when he had found evidence that radiation from a Big Bang would still be out there today, traveling through space, much like Herman and Alpher had concluded. Peebles found that if we were to look back far enough, we would actually be able to see the universe when it was still hot and on fire with this leftover radiation from the beginning of time. At this point, he teamed up with fellow astronomers David Wilkinson and Robert Dicke in hopes of building something powerful enough to detect this leftover cosmic radiation. Meanwhile, Penzias and Wilson were still searching for answers for this consistent low hum they had found. During a conversation with another astronomer, Penzias realized that they had discovered what could be the long sought-after evidence of the beginning of the universe, the leftover radiation from the actual Big Bang. They published their findings, and that was it. Astronomers around the world knew that Penzias and Wilson had discovered the markers of the Big Bang, the beginning of time. This discovery was so groundbreaking that Penzias and Wilson would actually go on to win a Nobel Prize for their work. The years that followed this discovery saw several ground-based attempts to further study the cosmic microwave background, and Soviets would launch a satellite in the early 80s with the capabilities of studying the CMB as well. But it was in the late 80s that we would see a new horizon when it came to detecting and unraveling the most ancient light in the universe. In November 1989, the COBE satellite was launched. Standing for Cosmic Background Explorer, the satellite was fitted with 3 powerful instruments designed to collect and measure data: a diffuse infrared background experiment to search for cosmic infrared background radiation, a differential microwave radiometer to map the cosmic radiation with high sensitivity, and a far infrared absolute spectrophotometer to compare the spectrum of the cosmic microwave background radiation with a precise black body. A black body is an idealized object that emits radiation based on temperature alone. Well, if the universe was a near-ideal black body, as the Big Bang Theory had proposed, it would have glowed with an orangish-white hue. And this would have been the first color to ever exist. COBE found that the CMB had a near-perfect black body spectrum. It also found that the universe was largely isotropic. It was very smooth with just tiny fluctuations overall. COBE measured that the CMB was just below 3 Kelvin, with small little differences throughout the sky, only about 1 part in 100,000 based on what COBE was able to detect. These tiny fluctuations show the differences in density during the early universe and seem to have produced the large-scale structure formations that we see in the universe today. The findings from the COBE data showed overwhelmingly to be in agreement with what the Big Bang model predicted. The radiation spectrum matched perfectly with the Big Bang model. By 1993, when COBE's mission had ended, its years in operation had provided a wealth of information and opened up the beginning of our universe in a way that no one thought possible just less than a century earlier. COBE was lauded as the beginning of cosmology as a precision science, and 2 of the head scientists would actually go on to win the Nobel Prize for their work. This might be a good time for me to tell you that if you're interested in winning the Nobel Prize, if you have any interest in cosmology or astrophysics, consider researching the CMB. It seems to have a penchant for giving its scientists Nobel Prizes. So far, COBE has had two successors, the WMAP and the Planck. WMAP was launched in 2001 and operated until 2010. Designed to improve upon the measurements taken by COBE, the WMAP satellite would allow astronomers to more accurately date the universe than ever before. They were able to give it an age of 13.77 billion years, with accuracy of within 0.5%. The WMAP was able to measure the shape of space, or the flatness of space, and they found that our universe has very, very minimal curvature. It is essentially flat. This gives cosmologists clues as to the eventual fate of our universe, a subject for an upcoming video. Using the data from the WMAP, scientists were able to calculate that about 4.6% of the universe is made up of normal matter. Less than 5% of the universe is stuff we can actually see and interact with. 24% dark matter and 71.4% dark energy. Furthermore, the WMAP was able to provide strong evidence for an inflationary period, something proposed by physicist Alan Guth in the 80s. According to NASA, what WMAP found was that the universe showed signs of growing a trillionfold in less than a trillionth of a second. The WMAP also captured clear images of a large cold spot in the direction of the Eridanus constellation, and it continues to trouble scientists to this day. More on that in a moment. The WMAP, like COBE, would see its head scientists receive Nobel Prizes. And by 2012, the research from the WMAP was the most cited in all of science, not just physics and astronomy, all of science. All while this is going on, in May of 2009, the WMAP successor, the Planck satellite, had been launched. The Planck mission sought to improve on the WMAP with even more precise measurements. It worked perfectly for over 2 years, allowing it to capture 5 full sky surveys. Planck carried a 1.5 meter primary mirror that was able to focus the CMB onto 2 extremely sensitive detectors, one high-frequency instrument made up of some 52 detectors, and a low-frequency instrument made up of 22 tuned radio receivers working on 4 frequency channels. It was able to measure the age of the universe with even more accuracy, landing at 13.8 billion years. It discovered nearly 200 galaxy clusters, dark gas, a new type of molecular gas, and was able to pinpoint more precise percentages of the amount of regular matter, and dark energy. Each of these missions to study the cosmic microwave background revolutionized how astronomers understood the age and evolution of the universe. Important information that lives within that faint signal left over from the last scattering has the power to rewrite how we see the early cosmos. There are currently proposals for the successor of COBE, WMAP, and Planck, all with the potential to answer more questions and create more mysteries, like this cold spot. First recorded by the WMAP during its first year of data collection, this spot just seems out of place. First of all, it's massive. It is one of the largest structures in the entire universe, and it's about 0.0007 Kelvin colder than the rest of the cosmic microwave background. It's actually much, much colder in some spots. Now, that might not seem like a lot to you, but that's actually quite statistically significant. It's significant because the cosmic microwave background is extremely uniform, and our best models for explaining the universe don't account for those types of fluctuations. It gets even weirder when you think about what this cold spot could be. Initially, it was thought that it was some type of error in the WMAP recording, but when scientists observed it with the Planck satellite and with similar values, they knew this was no fluke. Some suggested this exceptionally large area is due to something called cosmic texture, a type of topological defect of sorts. Its defect would have its origin during a phase transition. A phase transition that the universe underwent, for example, is when it cooled to just around 3000 Kelvin, and those first neutral atoms were able to form, allowing the cosmic microwave background to form. This cold spot would be a remnant of a phase transition in the early universe if it were the case, but as of 2017, there wasn't sufficient evidence to support this hypothesis, nor has there been any confirmation of cosmic texture. One possible explanation is that this is a supervoid. A void in space is where there are few or no galaxies present, but the known voids that are out there don't keep astronomers up at night quite like this one. If this is in fact a void, this is massive. Thousands of times larger than the other known voids, 1 billion light years across. I cannot express how massive and statistically improbable this cold spot is. It shouldn't be there based on the most well-supported models that are out there for our universe. But there are some suggestions that are even more crazy than the idea of it being cosmic texture or a super void. Some have suggested that this cold spot could actually be evidence of a parallel universe that came into contact with ours. Physicists such as Laura Mersini-Hutton have suggested that the large cold spot could in fact be an imprint of a parallel universe caused by quantum entanglement between our universe and another before inflation separated them. Others have suggested that it could be from a collision prior to inflation. As new missions to study the CMB are proposed, it's possible that we'll eventually have a good explanation for what this cold spot is. But until then, it's fun to think about parallel universes and possible collisions with them. At the beginning of this, I said that the cosmic microwave background was where I wanted to start. The first light in the universe. To me, it's because the CMB shows the power that light has, even when it's faded and stretched beyond the visible. It can give us important clues to so much about our cosmos. Because of light, we know today that we live in a universe that had a beginning. It's not existed forever, and it's certainly not static. Because of light, we know it's expanding. Because of the cosmic microwave background radiation, we know that the universe came into existence just under 14 billion years ago. We know that it's largely flat and that it has far more dark matter and dark energy than the type of matter that makes up you and me. Thanks to that old faded light and our ability to study it, we actually know what the first color to ever exist in the universe was. We've discovered hundreds of galaxy clusters, a new type of gas, and all of that from a faint, stretched out bit of light that died out almost 14 billion years ago. I actually recorded this a couple of times, but the files got corrupted, so I had to re-record it, so it's gonna be fun.